In video series part 1 of forces, we discussed what is meant by force, types of forces, the effects of forces, how to draw vectors, difference between vectors and scalars, and how to aid parallel and anti-parallel forces. Now in part 2 we are going to aid non-parallel vectors, in which we are going to discuss head-to-tail rule, parallelograms law, vectors addition, and we will also discuss some questions from past papers related to vectors addition. So let's start from head-to-tail rule. According to this rule, if we have two or more than two vectors and we want to add them, then first we take some starting point where we put our first vector according to the chosen scale. We draw the vector, then we take the second vector and we join the tail of the second vector with the head of the first vector. Then we join the tail of the third vector with the head of the second, and we similarly proceed till final vector. And finally we draw the tail of first vector with the head of last, which gives us the resultant. And resultant vector is a vector which is having the combining effect of all the vectors in the process of addition. In this way we get the resultant vector. Let's discuss the head-to-tail rule with an example. Consider three forces acting on a body as shown in the figure. One force is 10 Newton, which is along x-axis. The second force is 8 Newton, which is making an angle of 45 degrees with the x-axis. And the third force is 6 Newton perpendicular to the x-axis. Now what we do, first we scale the forces. We take a scale according to our own choice. For example, we consider that 2 Newton is same as 1 centimeter. Then 10 Newton will be 5 centimeter, 8 Newton will be 4 centimeter, and 6 Newton will be 3 centimeter. Now we draw the representative lines for these vectors. So this is the first vector along x-axis, the second vector 8 Newton, which is 4 centimeter, and the third one, which is 6 Newton or 3 centimeter perpendicular to the x-axis. Now let's join them by using head-to-tail rule. So the result we get is this. We draw all the vectors and we join the tail of the first vector with the head of last, and we get the resultant is equal to 10 centimeter. Now we are going to rescale it. As we took 1 centimeter as 2 Newton, so the resultant force will be 10 multiplied by 2 Newton, which is 20 Newton. And the direction is 37 degrees along x-axis. So this is an example which is solved with the help of head-to-tail rule. Now we consider another example in which there are two forces acting on a body, but both are perpendicular to each other. Both are 5 newtons. One is along x-axis, the other is along y-axis. And let's scale it in a way like 1 Newton is the same as 1 centimeter. Then we draw the first vector, which is 5 centimeter along x-axis. And now we put the tail of the second vector with the head of, we join with the head of first, and we get another vector. And finally we draw a vector which is joining the tail of the first with the head of last, and when we measure it, it is 7.1 Newton. So these are the examples which describe how to apply head-to-tail rule to join or to aid vectors. So this is all about head-to-tail rule. Now we consider two forces. One is 3 Newton and the other is 5 Newton acting on a single body in different directions. And the question is to find out the resultant of these forces. So how to find out the resultant? First we draw a line parallel to that red line, which is a reference line, and we draw a vector similar to 3 Newton, exactly parallel to 3 Newton. And then we draw a 5 Newton force which is exactly parallel to F2. In this way we get a parallelogram, and you can guess that now this is a parallelogram law vector addition. Now how to find out the resultant of these two forces? It is a very important point now. Join the starting point and the end point, and in this way we get the resultant. So this is parallelograms law vector addition, in which you are going to make a parallelogram of two forces. Now let's discuss some questions from past papers. Question number 1 is taken from May-June 2010 paper. Here is May-June 2010. This shows paper 2, variant 2, and this is the code for physics. So the question is, a journey consists of two displacements. The first is 500 meters and is a north direction, and the second is 200 meter in the east direction. In the space below, draw a vector diagram of these displacement. You are going to scale the diagram, or you're going to use a appropriate scale, for example ruler, and they were given as a geographical direction that the north you're going to take in this direction, which we always take. The south will be down, the east will be towards right, and the west towards left. So what to do? State the scale of your diagram. On your diagram, show the two displacements and the resultant displacement. Determine the size, that is the magnitude, and the direction of the resultant displacement. So there are 3 marks, and 1 mark is for each blank: scale, size, direction. Then there is another part. Another journey covers a distance of 700 meters. Describe how it is possible that this journey has no resultant displacement, and the mark is 1. This part is easy. Here you can write that if a body covers, suppose 700 meters, suppose 350 meters towards north, and for example it comes back 350 meters and reaches to the same point, then the distance covered will be 700 meters, but the displacement will be 0. That is 350 meters up, suppose, and 350 meters down, and the body reaches to its own starting point, then the displacement is 0 and the distance covered is 700 meters. So now let's watch the next video, in which we are going to describe how the question is solved. There are 2 forces given. One is 500 meters towards north, and the second is 200 meters towards east, and we need to find out the resultant and its direction. The solution is that first we make a scale, and for example the scale is, we take 50 meters as 1 centimeter, then 500 meters will be equal to 10 centimeters, and 200 meters will be equal to 4 centimeters. So we need to draw this towards north and this towards east. So let's draw it. Take a ruler and put it straight, and I mark it here from 1 to 11, and that gives me 10 centimeters towards north, because in the direction in the diagram it is shown that the north is up, which is always up. And now we need to take 4 centimeters towards east. So I am taking it from 1 till 5, because I am avoiding the dead end. So let me try it again. It will be 5 centimeters, sorry, 4 centimeters. It is 4 centimeters towards east. Now we join these two, and when we join them we get so it is still here, and that is nearly 10.8 centimeters. Put arrows here, and this is our resultant. So the resultant vector is 10.8 centimeters. We rescale it, 10.8 times 50 meters. So here 50 meters, and on multiplication we get 540 meters. This is the answer. That is the magnitude of the resultant. Now here is the direction. You need to find out this with the alpha protector, and this angle comes out to be nearly 22 degrees. That's it. Now let us consider another example, and this question is taken from physics paper 2, October-November 2013. The question says that a set of traffic lights hangs from the end of a metal cable. A horizontal chain pulls the traffic lights to the right so that they are above the middle of the road. This figure shows that in this direction is the chain, while here is a metal cable, and these are traffic lights. Now the weight of the traffic light is 240 Newton. The weight of this traffic light is 240 Newton. Two of the forces on the traffic lights are the tension in the horizontal chain, the tension in this chain, and the weight. And here the weight of these traffic lights. On figure 1.1, mark an arrow that represents the tension in the horizontal chain. So just put an arrow here, and that's it. And you will get what? You will get 1 mark. An arrow that represents the weight of the traffic lights. So here exactly from the center down, an arrow, and that shows what? The weight of the traffic light. So here is the weight, and here is the tension. Now next is the tension in the horizontal chain is 140 Newton. So this is equal to 140 Newton. And we know that the weight is how much? That is 240 Newton. So use a scale diagram to determine the size of the resultant of the weight and tension. State the scale used for the diagram. So here we are going to mention the scale used and the resultant force. And for this again we need to use head to tail rule or parallelogram law of vectors addition. Now let's watch in another video how this question can be solved. In this example, the traffic light has a weight of 240 Newton, which is in the downward direction, and the tension of the chain or string is 140 Newton towards right. We need to find out the resultant. So first we scale the problem, and here we suppose that 40 Newton is equal to 1 centimeter. Then 240 Newton will be equal to 6 centimeter, and 140 Newton will be equal to 3.5 centimeter. Now what you are going to do, you draw 6 centimeters in the downward direction because the weight is acting downward, and then you draw 3.5 centimeter in this direction. Now exactly parallel to 3.5 centimeter, you draw 3.5 centimeter here, and exactly parallel to this 6 centimeter in this direction. This is the starting point and this is the end point. Join them and we get resultant, which when you measure it, it is slightly more than 6.9 centimeter. Let us consider take it 6.9 centimeter. So the resultant is 6.9 centimeter, and rescale it 6.9 centimeter multiplied by 40. That is 6.9 to 40 gives you 276 Newton. That is the resultant. Now to see what is the direction of this, then the direction of this with the weight is this angle. You measure it and write that this much angle it makes with the resultant with the weight, or measure this angle, write that this much angle it makes with the tension. That's it.